Yeah, welcome to my channel. This afternoon I'll be treating you guys what we call route law, and I want you guys to pay mass attention to the class. And before we move to the class, route law was propounded or was established by a French chemist, Francois Marie Raoult, in 1887. So what is route law all about? First and foremost, I will be drawing a beaker to explain what route law is all about. So now, look at this particular beaker here now. I have this. I have some particles here. This arrow, this arrow, this arrow, this arrow. So now I want to use this to explain the vapor pressure before I will state the route law. When talking about this route law, you must understand in a nutshell that if I have A and B in this container, and those A and B are volatile liquids, and you should take note of one thing: the one that move out, which is this arrow here, is the what? They evaporate. Why the one that come inside there condense? So the rate of evaporation is equivalent to the rate of condensation. So let's state route law. What is route law? Route law states that the partial pressure of each component of an ideal solution or mixture is, or of a liquid is equal to the vapor pressure of the pure components multiplied by the mole ratio or fraction in the mixture. So look at this particular law, that the partial pressure of each component of an ideal solution or a mixture of liquid is equal to the vapor pressure of the pure component multiplied by the mole ratio of fraction in the mixture. So now I'll be using this graph to explain the meaning of this law. And before we move on, this ideal solution vapor pressure, which I have explained earlier, that if A and B are in a container or a beaker, if A is exposed to air, that is, if A and B are exposed to air, the particles that is going out, that is, they evaporate. Why those, if I should fill in the words, that particular beaker, it means that A and B condense at high vapor pressure, because I've added some water to it, to that particular container. So now, to the route law now, look at this particular graph you have here. So I have this, I also have this for the route law. So I'll be, after this graph now, then I'm moving to the derivation of route law, where I'll be proving the formula to use for route law. So first and foremost, we have to understand the meaning of this particular graph. So I have this. This here is the vapor pressure, and here I have my x. So x1 is equal to 1, x2 is equal to 0, x1 is equal to 0, x2 is equal to 1. So now I have my total partial pressure to be PA plus PB. So here now I have my P naught B here. So I also have my what? P naught A here. So this here will give us P B, and here I have my what? P A. So let me explain this particular graph with respect to Raoult law. And one thing you should know about Raoult law is that Raoult law itself talk about more on colligative properties. So now, looking at this x1 here, so the components, this x1 and x2 are the pure components I have here. So now, at this extreme end here now, to this place, I have my x-axis, while this place is my y-axis, which is the vapor pressure, and here is my pure component. So mind you, if my x1 is 1 here, my x2 is what? 2. From this end to this end, my x1 here is 0, my x2 here is what? 1. So it shows that from this end here to this place, we have 100% pure component. So from here to this place, we have decrease. And also from here to this place, we also have what? Decrease. But you should take note of one thing. If I'm moving my x1 to this place now, I can have 0.4 here for my x1. Why? Because my x2 is equal to what? 0. So it represents my P naught, which is this. And this one here, for x2 now, I can decide to move my pure components from this place now to this place. So if both sides has 1, and here also have what? 1, it means that Raoult law is not correct. So note, the pure component multiplied by the mole fraction. The x here is a mole fraction. Take note, the x here is a mole fraction. So now, don't forget I told you earlier that from this place to this place now, we have a pure component multiplied by this x, which is the mole fraction. So let me prove the law, that is the derivation of ideal gas. Mind you, from that place we have that our P, which is the total partial pressure, is PA plus PB. Before we move to this law, so I want to use this ideal solution. And what is that particular meaning of this ideal solution? Ideal solution make us to understand that they can be defined as a substance or a molecule which undergoes complete uniformity or cohesive force. That is, if a molecules or all molecules undergoes at the same time, they move in the same way. So that's the meaning of that particular cohesive force now. So now if I want to relate this ideal gas to the meaning of vapor pressure, where I use A and B in a container, it means that the intermolecular force between A and A, so to know the meaning of that cohesive force, B and B and A and B exerts at the same time. So the nature of the force in ideal solution, they move in uniformity. Are you with me now? So now let's state the Raoult law using the particular law to prove the Raoult law equation. So we said in an ideal gas, we are meant to know that the total pressure of a gas will give us this. So you must understand the concept of an ideal gas or Dalton's law of partial pressure to be able to relate it to what? Raoult law. So I have Pt is equal to Pa plus Pb, but Pa is equal to this. So we have Pa naught multiplied by the mole fraction of A, which is this. The next one, Pb is equal to Pb naught multiplied by the mole fraction of this. So I can decide to use whether it is equal to 1 to be the mole fraction of A at this end. Then whether it is equal to x is equal to 2 to be the mole fraction of what? This. So now let's replace this 2, or let's substitute these 2 here. So substitute. So I call this equation 1, I call this equation 2, I call this what? Equation 3. So substitute equation 2 and 3 to equation 1. Are you getting it now? So my PT is equal to P naught A multiplied by mole fraction of A plus P naught B multiplied by mole fraction of B. So now, in chemistry, we are meant to know that our mole fraction, which is this, if we add these two together, we're going to have 1, according to what you have here. If I should add this together and this, I'm going to also have what? 1 there. So I said mole fraction of A plus mole fraction of B is equal to 1. But XB, the mole fraction of B is equal to 1 minus the mole fraction of A. Then the mole fraction of A is equal to the mole fraction 1 minus what? Mole fraction of what? B. So I can decide to substitute either of the two into the formula. So it's that. With that, so I have that my PT. So let's substitute this. So we have that PT is equal to P naught A multiplied by this plus P naught B. So what is my XB? Because I'm to replace this one is equation 4, 5, 6, 7. So I have this to be what? So this here, my XB here, which is the mole fraction of B, is equivalent to what? 1 minus what? Mole fraction of A. So with that, you can say that I have 1 minus mole fraction of A, we close the bracket. So now let's open the bracket now. I can say the total partial pressure is P naught A plus this multiplied by this, I'm going to have this P naught B minus P naught B mole fraction of A. So with this now, we have to rearrange. We bring or collect like things. So with that now, I can have this, I can also have what? This. You can see that both have the same mole fraction. So with that, I can say that I have PT is equal to my, so we have this to be PA naught, this, minus PB naught, mole fraction of A, plus this. So now we have PT is equal to, what is common here we have what? Mole fraction of A, open the bracket, I have P naught A minus P naught B, close the bracket, plus P naught what? B. I have proved the Raoult's law that the partial pressure of each component of an ideal solution of a mixture of liquid is equal to the vapor pressure of the pure component multiplied by the mole fraction in the mixture. So I've proved what? Raoult's law. So now if we are solving any question in Raoult's law, you should consider